The comparative flight testing continues for 3 weeks. Different pilots, different scenarios, different altitudes and airspeeds. Each test adds layers of data, confirms or challenges initial impressions, builds a comprehensive picture of how these aircraft perform against each other when flown by skilled pilots who understand both machines. Lieutenant Commander Frederick Trapnell takes his turn in the Focke-Wulf. Trapnell is one of the Navy's most experienced test pilots, a man who has flown virtually every American fighter type and several captured enemy aircraft. His perspective carries weight when Trapnell says something about an aircraft's handling characteristics. People listen. He returns from his first flight in the German fighter with observations that echo Meyer's initial impressions. The Focke-Wulf is an impressive machine, sophisticated in ways that American fighters aren't. The single-lever throttle control, in particular, fascinates him. In American fighters, managing engine power requires constant attention to 3 separate controls: throttle, propeller, pitch, and mixture. Get the sequence wrong, and you risk engine damage or loss of power at a critical moment. The German system is automated. Push the throttle forward and the engine management system adjusts mixture and propeller pitch automatically, optimizing performance for the current flight regime. It's faster, simpler, and eliminates an entire category of pilot error. In the chaos of combat, when a pilot's attention is divided between enemy aircraft, friendly aircraft, altitude, airspeed, ammunition remaining, and a dozen other factors, anything that reduces mental workload is an advantage. But Trapnell also notes the Focke-Wulf's limitations. The control forces become heavy at high speeds. The ailerons stiffen up, making roll maneuvers difficult. The elevator requires significant force to pull the aircraft into tight turns. American fighters remain responsive and light on the controls, even at high speeds, a characteristic that proves critically important in combat maneuvering. The turning tests confirm what Meyer discovered. In a sustained turning fight, both the Hellcat and Corsair can turn inside the Focke-Wulf. Not by a small margin, by enough that the German fighter pilot is always behind, always chasing, never able to bring guns to bear. The test pilots fly engagement after engagement, and the pattern holds consistent. When a Hellcat or Corsair pilot sees a Focke-Wulf diving on him from above, the correct response is to turn hard into the attack, not to run, which plays to the German fighter's strengths, not to climb, which is suicide against an aircraft with superior power-to-weight ratio. Turn. Force a turning fight. In a single 360-degree turn, the American fighter will be behind the Focke-Wulf, in firing position, able to bring its 650 caliber guns to bear. The test data reveals something else, something that doesn't show up in specification sheets or performance charts. The Focke-Wulf requires precision flying. Its advantages, speed, climb rate, energy retention, only matter if the pilot can exploit them. That requires keeping speed up, maintaining energy, never getting slow or caught in a turning fight. It requires discipline, experience, and situational awareness. The Hellcat is more forgiving. It doesn't punish pilot errors as severely. Its flight characteristics are predictable and honest across its entire performance envelope. A pilot can focus on fighting the enemy instead of fighting the aircraft. For the US Navy, which was training thousands of new pilots and sending them into combat after relatively brief training periods, this characteristic was invaluable. The test pilots document everything: roll rates at different airspeeds, turn radii at different G loadings, acceleration times from cruise to maximum speed, climb rates at different altitudes, dive performance, control harmony, cockpit visibility, gun platform, stability, every metric that might matter in combat. They test the Corsair too, the Navy's other frontline fighter. The bent-wing Vought fighter had been in service longer than the Hellcat, but had initially struggled with carrier landing problems. The Marines flew it extensively from land bases, and it had compiled an impressive combat record in the Pacific and in the skies over the Solomon Islands. The Corsair proved slightly faster than the Hellcat, slightly better in the vertical, with a roll rate that matches the Focke-Wulf's. But like the Hellcat, it can outturn the German fighter. The same tactical principles apply. Don't run, don't climb, turn into the attack and use superior maneuverability to gain advantage. By April 1944, the testing phase is complete. The data has been compiled, analyzed, and organized into a comprehensive report that will be distributed to fleet commanders, training squadrons, and Tactical Development Units. The report's conclusions are clear and unambiguous. The Focke-Wulf 190 is faster than both American fighters in level flight. It climbs better. It possesses superior energy retention. Its armament, mixing 20mm cannons with machine guns, delivers more destructive power per trigger pull. But the American fighters are superior in combat. The report's language is precise and technical, but the meaning is clear. The FW-190 is an extremely simple airplane to fly and is designed for pilot convenience, but is not equal to the F-4UN or F-6F3 in combat. In general, whenever the F-4UN and the F-6F3 could not use the hit-and-run technique, it was best for them to close with the FW-190 in offense and defense to prevent it from getting in a position to make a high-speed, one-pass attack that would allow its pilot to take advantage of his firepower. The key phrase is, not equal in combat. Not in specifications, not in raw performance numbers. In combat, what matters isn't top speed or climb rate, but the ability to position your aircraft where you can kill the enemy while preventing him from killing you. The test pilots agree unanimously. Given a choice between flying a Focke-Wulf or an American fighter into combat, they would choose the American aircraft. Every time. Not because it was faster or more powerful, but because it gave them a better chance of surviving and winning. The irony of the test results becomes apparent when compared to the performance metrics that dominated pre-war fighter design philosophy. For decades, fighter designers had focused on speed and climb rate as the primary measures of combat effectiveness. The faster fighter, the thinking went, could control the engagement, choosing when to fight and when to disengage. This philosophy produced aircraft like the Focke-Wulf 190 and the Messerschmitt 109, fighters optimized for speed and climb performance. German tactical doctrine emphasized energy fighting, maintain speed and altitude advantage, dive on enemy aircraft with superior energy, make a high-speed firing pass, then use superior climb rate to regain altitude before the enemy can respond. It was an effective doctrine when executed properly. Luftwaffe pilots racked up extraordinary scores using these tactics against Soviet and Allied aircraft, but it required specific conditions to work. Altitude advantage to begin with, discipline to maintain energy instead of getting drawn into turning fights, and the ability to disengage when conditions weren't favorable. American fighter doctrine evolved differently, shaped by different requirements and different combat conditions. Navy fighters had to operate from carriers, which imposed unique constraints. They needed to be rugged enough to survive carrier landings. They needed to be easy enough to fly that pilots with relatively limited training could operate them safely. They needed range to find enemy targets far from the fleet and endurance to remain on station for extended periods. These requirements produced fighters that prioritized different characteristics, not ultimate speed, but sufficient speed, not maximum climb rate, but adequate climb performance, not the highest altitude ceiling, but enough altitude capability for the expected combat environment, and crucially, maneuverability, the ability to turn, to change direction quickly, to respond to threats from any angle. The Hellcat embodied this philosophy completely. Its maximum speed of 376 miles per hour wasn't exceptional by 1944 standards. The Focke-Wulf could do 408 miles per hour. The Messerschmitt 109 could reach 406. Even the Corsair was faster than the Hellcat. But the Hellcat's speed was sufficient for Pacific combat. Japanese fighters weren't significantly faster. More importantly, the Hellcat's other characteristics, its ruggedness, its maneuverability, its ease of handling, its powerful armament, its ability to absorb battle damage made it extraordinarily effective in the combat conditions it actually faced. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Patuxent River tests revealed that these same characteristics also made the Hellcat effective against German fighters, not because it matched their speed or climb performance, but because it could force combat conditions that negated those advantages. A Focke-Wulf pilot with superior speed and altitude could theoretically control the engagement. But if the American pilot turned into the attack, forcing a turning fight, the German pilot's advantages disappeared. The turn became an equalizer. In a 360-degree turn, speed differences mattered less than turn radius and turn rate. The Hellcat's superior maneuverability meant it completed the circle faster and tighter than the Focke-Wulf. In practical terms, this meant an American pilot who saw the attack coming and reacted correctly could reverse the situation from defensive to offensive in a single turn. This revelation had profound implications for fighter tactics and training. It meant that American pilots didn't need to avoid combat with German fighters. They didn't need to feel outmatched or inferior. They simply needed to understand the relative advantages of their aircraft and fly tactics that exploited those advantages. The British had learned these lessons the hard way, through combat experience and blood. When the Focke-Wulf first appeared over France in 1941, Spitfire pilots tried to fight it the way they'd fought Messerschmitt, 109s, running, diving, using speed to escape. It didn't work. The Focke-Wulf was faster in level flight and could catch diving Spitfires. British losses mounted alarmingly. Eventually, through trial and error and careful analysis of combat reports, the RAF developed effective counter-tactics. Turn into the attack. Force a turning fight. The Spitfire 5 couldn't outturn a Focke-Wulf reliably, but the Spitfire 9 could. Once British pilots understood this and had aircraft that could exploit it, the Focke-Wulf's dominance ended. The Americans now had the same knowledge without having to pay for it in blood. The Patuxent River tests had compressed years of combat experience into a few weeks of intensive flight testing. Navy pilots would go into combat against the Luftwaffe, understanding exactly what their aircraft could and couldn't do, and understanding exactly how to fight German fighters effectively. The first opportunity to apply these lessons came sooner than expected. In April 1944, the Royal Navy began preparations for Operation Tungsten, an airstrike against the German battleship Tirpitz, hiding in Norwegian fjords. The massive battleship represented a persistent threat to Allied convoys running supplies to the Soviet Union through the Arctic. As long as Tirpitz remained operational, the Royal Navy had to maintain powerful covering forces to counter the potential threat. The strike force would include Fairey Barracuda torpedo bombers, escorted by fighters. The Royal Navy's Fleet Air Arm had recently received American-built fighters through Lend-Lease, including Grumman Hellcats. No, 800 Squadron, flying from the escort carrier HMS Emperor, had just transitioned from obsolete Sea Hurricanes to F-6 F-3 Hellcats. The British pilots appreciated their new mounts immediately. Compared to the Sea Hurricane, the Hellcat was faster, better armed, and far more capable. It was also much easier to land on carriers, a critical advantage when operating in the rough seas common to North Atlantic operations. The Hellcat's wide-track landing gear and docile handling characteristics made carrier recoveries almost routine, even in challenging conditions. On April 3, 1944, the strike force launched. 42 Barracudas escorted by fighters Hellcats, Corsairs, and Wildcats headed for Kafjord, where Tirpitz lay anchored beneath anti-torpedo nets. The Germans had positioned the battleship in a narrow fjord with steep sides, making approach difficult and providing natural protection against air attack. The strike achieved complete surprise. The Barracudas came in low and fast, dropping bombs and torpedoes while German anti-aircraft batteries scrambled to respond. The escorting fighters strafed defensive positions and engaged any German aircraft that attempted to interfere. Lieutenant Commander Stanley Orr, leading 800 Squadron's Hellcats, later reported that the Hellcat proved to be an excellent gun platform during the strafing runs. The aircraft's stability and the positioning of its 650 caliber guns in the wings provided accurate fire against ground targets. Several direct hits were observed on Tirpitz, and while the battleship survived, it was damaged severely enough to require months of repairs. But the real test came 1 month later, on May 8th, when 800 Squadron encountered German fighters for the first time. The mission was another escort assignment, this time covering a shipping strike along the Norwegian coast. The weather was typical for the region: low clouds, intermittent visibility, rough seas below. The Barracudas found their targets, a small German convoy, and began their attack runs. Then the Luftwaffe arrived, a mixed formation of Messerschmitt 109Gs and Focke-Wulf 190, as from Jagdgeschwader 5, the specialized unit responsible for defending Norway. These were experienced pilots, men who had been flying combat missions in one of the war's most challenging environments for months or years. The German fighters had an altitude advantage and made their attack from above, diving on the British formation with speed and aggression. The first pass was devastating. One Hellcat exploded under the impact of 20mm cannon shells, the pilot killed instantly. The German fighters flashed past and began climbing for another attack. But the remaining Hellcat pilots reacted exactly as their training and the intelligence from Patuxent River tests dictated. They didn't try to run. They didn't try to climb after the German fighters. They turned hard into the next attack, forcing the German pilots to either press their attacks through a turning fight or break off and try again. Several German pilots chose to press. Fatal mistake. The Hellcats outturned them, reversing from defensive to offensive in seconds. Lieutenant Blythe Ritchie, a Scottish pilot with previous combat experience in sea hurricanes, found himself on the tail of a Focke-Wulf 190. He fired a burst from his .650 caliber guns. The German fighter staggered, then began trailing smoke. Ritchie fired again. The Focke-Wulf rolled inverted and went down, crashing into the Norwegian Sea. Other Hellcat pilots claimed 2 Messerschmitt 109s. The combat lasted perhaps 3 minutes from first contact to final German disengagement. When it was over, the British had lost 2 Hellcats, one to the initial surprise attack, possibly a second to anti-aircraft fire from the ships below. The Germans lost 3 confirmed fighters, possibly more damaged. The Luftwaffe pilots submitted claims for 3 Hellcats destroyed, but post-war analysis of loss records shows only 2 British aircraft failed to return. The German overclaiming was typical for air combat, where the chaos and confusion of battle makes accurate assessment nearly impossible. What matters is that the British pilots, flying an aircraft designed primarily to kill Japanese Zeros, had successfully engaged and defeated experienced Luftwaffe pilots flying 2 of Germany's best fighters. The combat report filed by Lieutenant Commander Orr noted that the Hellcats' maneuverability was crucial to the outcome. When German fighters attempted to engage in turning combat rather than hit-and-run tactics, they found themselves at a decisive disadvantage. The Hellcat pilots could turn inside the German attacks, could bring their guns to bear quickly, could maintain situational awareness throughout the engagement. More importantly, the Hellcat's rugged construction proved its worth. Several aircraft returned to the Emperor with battle damage that would have destroyed lighter aircraft. Cannon shell fragments, machine gun bullet holes. One Hellcat landed with damage to its wing structure that made the aircraft unflyable, but it had brought its pilot home alive. The Norwegian combats were not the only encounters between Hellcats and the Luftwaffe. In August 1944, U.S. Navy fighters saw combat over southern France during Operation Dragoon, the invasion of the French Riviera. 2 American escort carriers, USS Tulagi and USS Kassan Bay, carried F-65 Hellcat squadrons tasked with providing air support for the invasion forces. The newer F-65 variant incorporated various improvements over the earlier -3 model, a more powerful engine with water injection, refined aerodynamics, improved armament options. But the basic characteristics remained the same: rugged, maneuverable, easy to fly, heavily armed. On August 19th, Ensign Alfred Wood from Observation Fighter Squadron 1, flying from Tulagi, encountered 2 Heinkel He-111s south of Lyon. The German bombers were attempting to escape Allied air superiority over the invasion beaches and reach the relative safety of German-controlled territory further north. Wood attacked from above and behind, the classic fighter approach. His .650 caliber guns hammered into the first Heinkel, raking the fuselage and wing. The German bomber staggered, its right engine erupting in flames. Wood shifted his aim to the second, He-111, which was attempting to evade by diving toward a cloud layer. He followed, maintaining firing position, his tracers walking across the bomber's wing route and center fuselage. Both Heinkels went down. Wood returned to Tulagi to report 2 confirmed kills, bringing his personal score to a level that would eventually make him one of the few Navy pilots with victories against both Japanese and German aircraft. But the more significant engagement occurred on August 20th, when Hellcats from Fighting Squadron 74 encountered Luftwaffe fighters over the invasion area. The German aircraft were a mixed formation of Messerschmitts and Focke-Wulfs, attempting to attack Allied shipping offshore. The Hellcat pilots engaged aggressively, using the tactics that had proven effective in the Pacific and that the Patuxent River tests had validated against German fighters. Turn into the attack. Force a maneuvering fight. Don't let the German fighters use their speed and climb advantages. The engagement was brief but decisive. The American pilots claimed multiple German fighters were destroyed for no losses in air-to-air combat. Several Hellcats took damage from anti-aircraft fire from ships both Allied and German, but all returned safely to their carriers. Over the 13 days of Operation Dragoon, The two American Hellcat squadrons flew hundreds of sorties. They lost 11 aircraft total, with most losses attributed to anti-aircraft fire rather than air combat. They were credited with destroying 8 German aircraft in air-to-air combat and wreaking havoc on German ground forces, destroying or damaging hundreds of vehicles and dozens of locomotives. Rear Admiral Thomas Trowbridge, commanding the British naval forces supporting the invasion, specifically commended the American Hellcat squadrons for their effectiveness. In his after-action report, he noted that the Hellcat had proven itself equally capable against European and Pacific opposition, a tribute to the aircraft's versatile design and the quality of American pilot training. The final comparative evaluation of Allied and Axis fighters came in late 1944 when the British Royal Aircraft Establishment compiled comprehensive performance data on virtually every significant fighter aircraft of the war. They had access to captured German fighters, Japanese fighters, and Italian fighters. They could compare these directly with British, American, and Soviet types. The results were published in a classified technical report that ranked fighters across multiple categories: speed, climb rate, maneuverability, armament, visibility, ease of handling, combat effectiveness. The Hellcat didn't rank first in any single category, but it ranked in the top tier in most categories and had no significant weaknesses. More tellingly, when test pilots were asked which fighter they would prefer to fly in combat, the Hellcat consistently ranked at or near the top, not because it was the fastest or the most heavily armed, but because it gave pilots the best combination of capabilities and the best chance of surviving and winning combat engagements. Captain Eric "Winkle" Brown, the Royal Navy's most experienced test pilot and a man who flew virtually every significant aircraft of World War II, offered his assessment in the years after the war. He compared the Hellcat directly to German fighters and concluded that while the German aircraft had performance advantages in specific areas, the Hellcat was the superior combat aircraft. His reasoning was instructive. In combat, Brown argued, raw performance mattered less than combat effectiveness. A faster aircraft wasn't necessarily better if that speed came at the cost of other characteristics. The Focke-Wulf was faster than the Hellcat, but Brown noted that in actual combat scenarios, the Hellcat pilot could force conditions that negated that speed advantage. Brown also emphasized the importance of pilot workload. German fighters required constant attention to engine management, fuel mixture, propeller pitch, and other technical details. The Hellcat automated most of these functions, allowing the pilot to concentrate on fighting rather than flying. In the chaos of combat, this difference was often decisive. His final judgment: in a one-on-one engagement between a Hellcat and a Focke-Wulf 190 with equally skilled pilots, the outcome would depend primarily on tactics and circumstances rather than raw aircraft performance. The German fighter had advantages, but they weren't decisive. The American fighter had different advantages, equally significant. Either pilot could win, depending on how they fought. But Brown also noted that combat was rarely one-on-one. American pilots usually had numerical superiority, better training, better situational awareness through superior radio communication, and the knowledge that their aircraft could absorb damage that would destroy German fighters. These factors, combined with the Hellcat's inherent capabilities, gave American pilots a decisive advantage in actual combat conditions. The broader implications of the Patuxent River tests and subsequent combat experience extended beyond simple aircraft comparisons. They revealed fundamental truths about fighter design and combat effectiveness that would influence aircraft development for decades. First, they demonstrated that optimization for a single characteristic, speed, climb rate, maneuverability, was less effective than balanced design. The Hellcat wasn't exceptional in any single area, but its combination of characteristics made it extraordinarily effective in combat. Second, they showed that ease of operation and forgiving handling characteristics were combat multipliers. An aircraft that was difficult to fly or that punished pilot errors was less effective in combat than one that allowed pilots to focus on tactics rather than aircraft handling. Third, they proved that ruggedness and survivability were critical factors in overall combat effectiveness. The ability to absorb battle damage and continue flying, to bring damaged aircraft back to carriers, to protect pilots from enemy fire. These characteristics directly influenced combat outcomes, even though they didn't appear in performance specifications. Fourth, They validated the importance of superior pilot training and tactical doctrine. American pilots understood their aircraft's capabilities and limitations. They flew tactics that exploited their advantages while minimizing their weaknesses. This knowledge, combined with good aircraft, produced consistent victories. The Hellcat's 19-to-1 kill ratio wasn't an accident or a statistical anomaly. It was the result of deliberate design choices that prioritized combat effectiveness over raw performance, combined with excellent pilot training and sound tactical doctrine. The aircraft was good enough at enough things to allow well-trained pilots to win consistently. By war's end, Hellcats had destroyed 5,223 enemy aircraft, more than any other Allied naval fighter. They had compiled this record in just over 2 years of combat operations, flying from carriers in the Pacific, from carriers in European waters, from land bases in various theaters. They had faced Japanese Zeros, Oscars, Tonys, Jacks, and Georges. They had faced German Messerschmitts, Focke-Wulfs, and Heinkels. They had dominated wherever they fought. Production totaled 12,275 aircraft, all built at Grumman's Long Island facility. At peak production, the factory completed one Hellcat every hour, around the clock. These aircraft equipped dozens of Navy and Marine Corps squadrons, trained thousands of pilots, fought in every major Pacific campaign from mid-1943 through the war's end. The captured Focke-Wulf that started this story ended its days as a training aid and museum piece. It had served its purpose, revealing truths that saved American lives and confirmed the validity of American fighter design philosophy. The test pilots who flew it gained knowledge that they passed on to combat pilots, who used that knowledge to fight more effectively and survive more consistently. The acceleration is immediate and visceral. Despite weighing nearly 9 tons, the Lightning surges forward with authority that shocks everyone watching. The twin 1,600 horsepower engines, even running on suboptimal fuel, produce thrust that overwhelms the aircraft's mass. Shibata watches the tail lift off the ground. Within seconds, the tricycle gear configuration means there's no tail to hold down, no critical transition moment where a pilot must balance rudder and elevator to prevent a ground loop. The P-38 simply accelerates in a straight line, gaining speed with mechanical inevitability. At 90 knots, approximately 103 miles per hour, Minobi eases back on the control column. The nose lifts smoothly, the main gear leaves the runway, and the Lightning climbs away from Rabaul at a rate that makes Shibata recalculate his estimates even as he watches. 2,800 feet per minute, perhaps 3,000. A Mitsubishi Zero climbs at approximately 3,000 feet per minute when light and flown aggressively. The P-38, carrying full fuel and ammunition, climbing at a conservative angle, matches it. And this is at sea level, where the Allison's turbochargers provide no advantage. At altitude, the performance gap will only widen. Minobi banks left over Simpson Harbor and continues climbing. The sound of the engines fades as he gains altitude, becoming a distant drone, then silent. The engineers stand on the tarmac, watching the Lightning shrink to a speck, then disappear into the morning haze. Now there is nothing to do but wait. Inside the cockpit, Minobi is methodically testing the aircraft's handling characteristics. He starts conservatively, gentle turns, shallow climbs, basic maneuvers to understand the control forces and response rates. The ailerons are heavy, much heavier than a Japanese fighter. Rolling into a turn requires deliberate physical effort. The rudder pedals are similarly stiff. Everything about the P-38 demands strength rather than finesse. At 5,000 feet, he levels off and accelerates. 250 miles per hour, 275, 300. The Lightning is not yet breathing hard. The controls remain responsive, firm but not overly heavy. There is no buffeting, no tendency to yaw or pitch. The aircraft simply flies, solid and stable, with none of the twitchiness that characterizes lighter Japanese designs. Minobi pushes the nose down slightly and continues accelerating. 320 miles per hour, 350, 380. At this speed, a Zero would be approaching its structural limits, the airframe beginning to shake, the controls becoming dangerously light. But the P-38 feels planted, confidence, built with margins that allow for speed without compromise. He pulls back into a climb, converting speed to altitude. The Lightning rises through 10,000 feet, 12,000, 15,000. The air grows thinner, but the engines don't seem to notice. This is where the turbochargers earn their complexity, maintaining manifold pressure as atmospheric pressure drops, forcing air into the cylinders with mechanical insistence. At 15,000 feet, Minobe levels off again and makes a discovery that will feature prominently in his report. The controls have changed character. The heaviness he felt at low altitude has transformed into precision. The ailerons, which required muscle to move near the ground, now respond with crispness. The aircraft's weight, which seemed like a liability during takeoff, now provides stability that Japanese fighters lack at altitude. There is no wandering, no tendency to pitch or yaw in turbulence. The P-38 simply goes where it's pointed and stays there until told otherwise. This is not how Japanese fighters behave. The Zero, the Hayabusa, even the newer designs, they're all light, responsive, sensitive to control inputs. They reward skilled pilots and punish mistakes. They're thoroughbreds that require constant attention. The P-38 is a workhorse. It doesn't require skill so much as competence. It forgives errors. It provides stability that makes instrument flying, formation flying, long-range navigation, all the mundane but critical tasks of air combat dramatically easier. Minobe advances the throttles to maximum power and times the acceleration. At 15,000 feet, the Lightning reaches 400 miles per hour in level flight. This is 50 miles per hour faster than the maximum speed of the Zero at optimal altitude. And the P-38 can sustain this speed indefinitely, limited only by fuel, while the Zero must dive to reach it briefly. He thinks about what this means in combat. A P-38 pilot can engage when advantageous and disengage when not. He can chase down Japanese bombers with impunity. He can attack, break off, climb away, and there is nothing, absolutely nothing that a Zero pilot can do to prevent it. The speed differential is insurmountable. Japanese pilots have been reporting this for months. Intelligence has documented it, but experiencing it, feeling it through the controls, understanding it in 3 dimensions rather than on paper, this is different. Minobe tests the turning performance. At 400 miles per hour, he rolls into a 60-degree bank and pulls. The Lightning turns, but the radius is wide, much wider than a Zero at equivalent speed. This is expected. Light aircraft turn tighter. It's physics. But then he notices something the intelligence reports haven't captured adequately. The P-38 doesn't bleed speed the way Japanese fighters do. In a sustained turn, the Zero slows rapidly, its light wing loading working against it. The pilot must either accept the speed loss or reduce the turn rate. The Lightning maintains speed through the turn. The twin engines produce enough thrust to offset the drag. The result is a paradox. Yes, the Zero can turn inside the P-38 inches, a snapshot comparison, but in a sustained engagement, the Lightning retains energy. It can make multiple turns without becoming vulnerable. It doesn't trap itself in a low-speed fight. This is a different kind of aerial warfare philosophy. Japanese doctrine emphasizes the decisive turning engagement. Get close, outturn the opponent, bring guns to bear. American doctrine, as embodied in the P-38, emphasizes energy management, maintain speed, control the engagement geometry, never get slow enough to be vulnerable. Both approaches work, but only if your aircraft supports them. And increasingly, Japanese fighters are encountering American aircraft that simply won't engage on Japanese terms. Minobe climbs to 20,000 feet. The engines are still producing power smoothly, though he can feel slight roughness that he attributes to the lower octane fuel. At this altitude, he knows Japanese fighters begin to struggle. The Zero's Nakajima Sakai engine is rated for only 1,100 horsepower at takeoff, and by 20,000 feet, it's producing perhaps 700. The Allison V-1710s are rated for 1,600 horsepower at takeoff and maintain that power to 25,000 feet with turbocharging. At 20,000 feet, each engine is still producing over 1,400 horsepower. The math is brutal. At altitude, the P-38 has twice the power-to-weight ratio of the Zero, twice the climb rate, 50% more speed, and equal or better range due to larger fuel capacity. He performs one final test, a high-speed dive. This is where many aircraft reveal their weaknesses: flutter, compressibility effects, structural failures. Minobe rolls inverted and pulls through to a vertical descent. The airspeed indicator climbs rapidly. 420 miles per hour, 440, 460. At 480 miles per hour, he feels a slight buffeting through the controls, the onset of compressibility as the aircraft approaches the speed of sound at altitude. But there is no flutter, no alarming vibration, no tendency for the aircraft to pitch or roll uncommanded. He pulls back firmly, loading the airframe to approximately 4 Gs, and the Lightning arcs smoothly out of the dive, the structure absorbing the loads without complaint. By the time he levels off at 10,000 feet, he has been flying for 1 hour and 45 minutes. His assessment is complete. He has seen everything he needs to see. He turns back toward Rabaul and begins his descent. On the ground, Shibata has been pacing the edge of the runway for the past hour. The other engineers are nearby, some sitting in the shade of a palm tree, others standing and watching the sky. No one speaks much. They're all thinking the same thoughts, performing the same calculations, reaching the same uncomfortable conclusions. At 08:15, someone spots the Lightning returning from the north. The distinctive twin-boom silhouette is unmistakable. Minobi enters the traffic pattern at 1,000 feet, configured for landing gear down, flaps extended, and brings the P-38 inches for a smooth touchdown. The tricycle gear absorbs the impact with barely a bounce. He rolls out, turns off the runway, and taxis to the parking area. The engines shut down one at a time. The propellers windmill to a stop, and then there is silence, broken only by the ticking of cooling metal and the distant sound of waves. Minobi sits in the cockpit for 5 minutes. He removes his helmet and goggles. He wipes sweat from his face. He stares at the instrument panel, at the throttle quadrant, at the gun sight mounted on the windscreen frame. When he finally climbs out, Shibata is waiting at the base of the ladder. Well? Minobi's face is expressionless. He pulls off his gloves and tucks them into his belt. Then he says, very quietly, "We cannot build this." The debriefing takes place in a sweltering tent at the edge of the airfield. 6 men crowd around a folding table covered with technical drawings, photographs, and handwritten notes. Outside, the temperature climbs toward 90 degrees Fahrenheit. Inside, it's at least 10 degrees hotter. No one notices. Minobi speaks for 30 minutes without interruption, describing every aspect of the flight in methodical detail. The other engineers take notes. Occasionally, someone asks a clarifying question. Mostly, they listen. When Minobi finishes, Shibata begins his structural analysis. He has spent the past 2 days measuring, calculating, and comparing the P-38's construction to Japanese practice. His findings are comprehensive and damning. The airframe, he begins, uses aluminum alloys we cannot produce in quantity. The primary structural members appear to be 24 ST alloy, approximately equivalent to our extra super duralumin, but with more consistent material properties. The skin panels are 75 ST, which we can approximate, but our version has 20% more variability in tensile strength. He flips through his notes. The riveting is precision work, flush rivets throughout, countersunk to tolerances of 5/1000ths of an inch. Our production methods achieve approximately 10/1000ths of an inch, which causes drag and potential stress concentration points. The difference seems minor. Across 10,000 rivets, it compounds. One of the Mitsubishi engineers interrupts. Can we adopt their methods? We can, Shibata says, but it would reduce production rates by approximately 30%. We would need to retool our entire manufacturing process, retrain our workers, and accept significantly slower output, and we would still lack the alloy quality. He continues. The engines are the critical component, 1,600 horsepower each, sustained. Our most powerful production engine is the Nakajima Homare, rated for 1,800 horsepower, but the Homare achieves that power only at emergency settings, for limited duration, and reliability remains problematic. The Allison maintains 1,600 horsepower continuously at specified RPM. Why? Someone asks. Cooling, Shibata says. The Allison is liquid-cooled, with a sophisticated radiator system and coolant mixture that maintains stable operating temperatures even at high power settings. And the turbochargers. This is critical. The turbochargers maintain manifold pressure at altitude, compensating for thin air. Our fighters lose 30 to 40% of their power by 20,000 feet. The P-38 loses almost nothing. He pauses, then adds, we have no turbocharger program that approaches this level of sophistication. The Navy has experimented with turbo-superchargers, but reliability is poor and production is limited. We are years behind. The third issue is materials beyond the airframe. The electrical system uses insulation that remains flexible at temperature extremes. The hydraulic lines use synthetic rubber seals that don't degrade in tropical climates. The fuel system includes self-sealing tanks lined with vulcanized rubber technology, Japan acquired from Germany, but has not implemented widely due to rubber shortages. Every component reveals the same pattern. American engineers designing with margin, building in redundancy, using materials without concern for scarcity, because scarcity is not their constraint. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. One of the Kawasaki engineers raises a fundamental question. If we cannot build this aircraft, can we build something equivalent? A different design that achieves similar performance? Shibata considers this carefully. In theory, yes. We could design a twin-engine fighter with comparable speed and climb rate, but we would face the same material constraints: the high-grade aluminum, the high-octane fuel, the powerful, reliable engines, and we would sacrifice our current advantage in maneuverability, which is the only area where our fighters remain superior. So we continue optimizing what we can build, Minobe says. Lighter, more maneuverable fighters that can outturn American aircraft at low altitude. Yes, Shibata agrees, but that strategy only works if we can force engagements at low altitude. The P-38 pilot controls the engagement. He can refuse combat, climb away, and attack from above. Our advantages become irrelevant if we cannot bring them to bear. There is a long silence. Everyone in the tent understands the implication. Japanese aerial doctrine for the past 15 years has been built on the assumption that agility and pilot skill can compensate for deficiencies in other areas. The P-38 demonstrates that this assumption has limits. Speed, power, and altitude performance create options that maneuverability cannot counter. Shibata spends the next 3 days compiling his findings into a formal report. He works late into each night, writing by lamplight in his quarters, cross-referencing measurements and calculations, trying to be thorough and objective. The report will go to Tokyo, where it will be read by staff officers and engineers, and possibly influence future aircraft development. He knows it won't change the fundamental problem. The report is 47 pages, typed on thin wartime paper using a portable typewriter that skips occasionally. It includes detailed technical drawings, performance calculations, and material analyses. Shibata attaches photographs of key components: the turbochargers, the main wing spar, the engine mount structure. The conclusion appears on page 47. The P-38 Lightning represents a design philosophy predicated on industrial capacity and material availability that the Empire does not possess. Its performance advantages derive not from revolutionary aerodynamics, but from engineering, margin, heavier structures, more powerful engines, and redundant systems that assume unlimited access to high-grade materials and fuel. Japanese doctrine emphasizes efficiency and optimization within constraints. American doctrine, as evidenced by this aircraft, emphasizes overwhelming capability without regard to constraint. We cannot replicate this approach. Any attempt to do so would consume resources better allocated to incremental improvements of existing designs and increased production volume of proven types. He adds a final paragraph. The strategic implication is clear. We are not engaged in combat with an enemy possessing marginally better technology. We are engaged with an enemy whose industrial base permits them to design and produce aircraft, incorporating capabilities we cannot match with available resources. This is not an engineering problem that superior design can solve. It is a resource problem that affects every aspect of our aircraft development program. Shibata reads the conclusion 3 times before sealing the report. He knows it sounds defeatist. He knows it will not be well received. But it is accurate, and accuracy is what has been requested. He handed the report to Lieutenant Colonel Sakai on March 15th. Sakai reads it overnight and summons Shibata the following morning. "This is pessimistic," Sakai says. "This is factual," Shibata replies. "The minister will not appreciate your conclusions." The minister requested an engineering evaluation. "I have provided one." Sakai stares at him for a long moment, then nods. "It will be forwarded through channels, along with Commander Minobe's flight test report and the other engineers' assessments. And the aircraft itself? We will continue test flights for another 2 weeks. After that, it will be shipped to Japan for detailed examination. This never happens. On April 3, 1943, during a test flight piloted by a different aviator, a younger man, less experienced, eager to push the Lightning to its limits, the left Allison engine failed catastrophically. The turbocharger disintegrates, sending turbine blades through the oil cooler and severing hydraulic lines. The pilot manages to land the P-38 safely on one engine, demonstrating exactly the redundancy American designers intended, but the damage is severe. There are no spare parts. No way to repair an Allison V-1710 engine in Rabaul with Japanese tools and materials. The Lightning is grounded permanently. Over the next 2 weeks, Japanese engineers systematically dismantled the aircraft. The engines are created and sent to Nakajima for detailed analysis. The turbochargers go to a specialized research facility near Tokyo. The propellers, the landing gear, the gun sights, the radios, every component is catalogued, packed, and shipped. The airframe itself is cut apart for scrap metal. By May 1, 1943, nothing remained of the P-38 that Lieutenant Hoyt Vandenberg flew to his death except photographs, measurements, and reports filed in archives. The reports reach Tokyo in late April. They are read, discussed, and filed. Some of the technical information influences ongoing design projects. The Nakajima Ki-84 Hayate, introduced in 1944, incorporates lessons learned from studying the P-38 structure, particularly in fuselage construction and landing gear design. But the strategic conclusions are ignored, not because they are wrong. Everyone who reads Shibata's report recognizes its accuracy. But acknowledging the resource disparity means acknowledging that Japan cannot win a protracted industrial war against the United States. And in April of 1943, with Guadalcanal recently lost and the Solomons campaign consuming men and materiel at unsustainable rates, Japanese military leadership cannot afford to accept this reality. So they focus on what they can control: incremental improvements, better training, tactical innovations, the spiritual superiority of Japanese pilots, anything except the fundamental problem that Shibata identified on page 47 of his report. Captain Tsuneo Shibata returns to Nakajima's Musashino plant in late April 1943. He resumes his work on the Ki-84 program, applying knowledge gained from the P-38 where possible, working within constraints that grow tighter month by month as American submarines strangle Japan's resource imports. The war continues for another 28 months. Shibata remained at Musashino until February 19, 1945, when American B-29 bombers from the 21st Bomber Command destroyed the factory in a daylight precision raid. 341 superfortresses drop over 2,000 tons of incendiary and high-explosive bombs, gutting the facility and killing over 600 workers. Shibata survives. He is transferred to Fuji Heavy Industries, where he works on increasingly desperate projects, the Nakajima Kicker jet fighter, a design copied from German Mi-62 plans, using engines that barely work and materials that barely exist. The Kicker flew once, on August 7, 1945. One day before the atomic bomb destroys Nagasaki, the test pilot reports that it handles well but lacks power. There is no fuel for further testing. The war ends. In the aftermath of Japan's surrender, Tsuneo Shibata finds himself in a country that no longer exists in the form he knew. The empire has collapsed. The military has been dissolved. The factories that consumed his professional life are ruins or being dismantled by occupation forces. He is 33 years old, trained in a specialty that has no peacetime application in a nation forbidden from building military aircraft. He returns to what remains of his family home in Tokyo's Setagai Ward. The house survived the firebombing, though the neighborhood around it is largely ash and rubble. His wife and 2 children are alive. This makes him luckier than most. For 6 months, he does odd work. Translation for occupation authorities. His technical English is adequate. Tutoring students in mathematics and physics. Anything to feed his family while Japan stumbles toward some uncertain future. Then, in March of 1946, he received a letter from the United States Strategic Bombing Survey. They are interviewing Japanese engineers and military personnel, documenting the war from the Japanese perspective, and compiling technical assessments of Japanese aircraft and industrial capacity. Someone has recommended Shibata as knowledgeable about captured American aircraft. The interview takes place in a requisitioned office building in central Tokyo. 2 American officers and a translator, though Shibata's English proves sufficient for technical discussion. They ask about his work at Nakajima, about specific aircraft types, about manufacturing methods and material shortages. Then, one of the officers produces a document from a folder. Shibata recognizes it immediately, his own report on the P-38 Lightning, written in March of 1943 at Rabaul. Someone has translated it into English. The officer marked several passages with a pencil. "You wrote here," the officer says, reading from page 47, "that the P-38 represented industrial capacity Japan did not possess. You concluded that this was a resource problem, not an engineering problem. Can you elaborate?" Shibata chooses his words carefully. He is speaking to representatives of the victorious power, in a country under occupation, about conclusions that were considered defeatist by his own government. But the question is technical, not political, and he answers honestly. "Japanese aircraft design," he begins, "was constrained by material scarcity from the beginning. We had limited access to high-grade aluminum alloys, to high-octane aviation fuel, to rare metals like molybdenum and tungsten. So, our engineers became experts in optimization, doing more with less, building lighter structures, designing engines that produced adequate power on lower-octane fuel, eliminating any component that was not absolutely essential." He pauses, organizing his thoughts. This philosophy produced excellent aircraft within those constraints. The Zero was perhaps the finest carrier fighter in the world in 1941, considering its range, maneuverability, and firepower. But it was optimized for specific conditions. When American fighters like the P-38 appeared, aircraft designed without those constraints, with heavier structures, more powerful engines, redundant systems, our advantages disappeared. "You're saying American aircraft were over-engineered?" the officer asks. "No," Shibata says firmly. "I'm saying they were engineered for different assumptions. American designers assumed that weight could be overcome with power. That complexity could be managed with better training and maintenance infrastructure. That redundancy was worth the cost because it meant more pilots returned alive. These assumptions were correct, but only because America had the industrial capacity to support them." The officer makes notes. "And Japan could not adopt these design principles. We could adopt them in theory, but we lacked the materials to implement them at scale. Building one prototype with heavy structure and powerful engines is possible. Building 10,000 is not, if you don't have the aluminum, the fuel, the factory capacity, the electrical grid to power the factories." Shibata's voice is level, factual. "By 1943, I understood that we were fighting an industrial war with inadequate industry. The P-38 made this clear. It was not the best fighter aircraft of the war. Other American designs were better, but it was the first I examined that revealed the true scale of disparity." The interview continues for 2 hours. When it concludes, the American officer thanks Shibata for his candor and asks if he would be willing to consult on additional technical matters. Shibata agrees. Over the next year, he provided testimony for several USSBS reports, contributing to documents that will shape American understanding of Japanese industrial limitations and the effectiveness of strategic bombing. The work pays adequately and occupies his mind. But it is strange, unsettling work cataloging the failures of the system he served, explaining in careful technical language how and why Japan lost the technological war before the shooting war was truly joined. In 1947, as Japan begins its slow reconstruction under American occupation, aircraft manufacturing resumes, but not military aircraft. The restrictions are absolute. Shibata finds employment with Fuji Sangyo, a company attempting to transition from military to civilian production. They manufacture scooters, small engines, eventually automobiles. It is prosaic work, far removed from the cutting edge of aviation, engineering. But it is honest employment in a country desperate for both. He has not spoken publicly about the war for many years. In Japan's immediate post-war period, there is little appetite for examining military failures in detail. The focus is survival, reconstruction, building something new from the ashes. Former military engineers keep their heads down and do civilian work, but in 1952, something unexpected happens. Shibata is at a newsstand in Shinjuku when he sees a photograph in an American aviation magazine. A restored P-38 Lightning, polished to mirror brightness, on display at an air show in California. The caption identifies it as one of approximately 50 Lightnings still flying, preserved by collectors and aviation enthusiasts. He buys the magazine and takes it home. That evening, he sits at his kitchen table and stares at the photograph for a long time. The twin booms, the tricycle landing gear, the distinctive profile that he last saw being disassembled for scrap at Rabaul in April of 1943. He thinks about Lieutenant Hoyt Vandenberg, who died in the jungle so this machine could fall intact into Japanese hands. He thinks about the test flights, the measurements, the report he wrote that nobody wanted to believe. He thinks about the thousands of Japanese pilots who encountered P-38 seconds in combat and learned, often fatally, the same lessons he documented in his engineering analysis. And he thinks about the fundamental asymmetry that defined the Pacific War. Japan fighting with excellence and determination within severe constraints. America fighting with adequate skill and overwhelming resources. Neither side was wrong in their approach, both sides logical within their contexts, but only one side capable of sustaining industrial warfare across an ocean. The photograph troubles him in ways he cannot quite articulate. It represents something about the war that remains difficult to process even 7 years later. Not a defeat that is obvious, accepted, unchangeable, but the specific nature of the defeat, the way that engineering skill and pilot courage proved insufficient against sheer industrial capacity. He files the magazine away and returns to his work, designing automotive components. The past is the past. Japan is building a different future. But the questions linger. In 1973, 30 years after his evaluation of the captured P-38, Shibata is 61 years old and approaching retirement from Fuji Heavy Industries. The company has grown substantially, evolving into Subaru Corporation, producing automobiles and aircraft components. Japan's post-war economic miracle has transformed the country from occupied ruin to industrial powerhouse. The scarcity that defined the wartime period is long past. A researcher from NHK Japan's Public Broadcasting Corporation contacts him about a documentary series on the Pacific War. They are interviewing veterans and engineers, collecting oral histories before that generation passes. Would he be willing to discuss his wartime work? Shibata agrees, though with reluctance. He has spent 3 decades not discussing the war in detail. But he is old enough now that the past feels less personal, more historical, and perhaps there is value in documenting what actually happened, as opposed to the myths that have accumulated. The interview is conducted in his home in Nerima Ward, Tokyo. The researcher is young, perhaps 30 years old, with no direct memory of the war. She asks about his education, his work at Nakajima, the specific aircraft programs he contributed to. Then she asks about Rabaul and the P-38. Shibata had not expected this. The report he wrote was filed in military archives, classified, presumably lost or destroyed in the war's final chaos. But the researcher has found a copy declassified by the Japanese government in 1968, part of a broader release of wartime documents. She has read it. She has questions. "You wrote," she says, consulting her notes, "that Japan was fighting an enemy with better factories, not better engineers. 30 years later, do you still believe this?" Shibata considers the question carefully. "I believe it was true in 1943. Whether it remains true today is a different question. Japan has rebuilt its industrial capacity. We manufacture automobiles, electronics, and precision machinery. We do so efficiently and with high quality. But this was possible because we learned from defeat. We studied American manufacturing methods. We adopted their emphasis on quality control, standardization, and continuous improvement." He pauses, then continues. "The P-38 taught me that engineering exists within context. The best design is meaningless if you cannot produce it. The cleverest optimization is irrelevant if your opponent can overwhelm it with quantity. These seem like obvious truths now, but in 1943, they contradicted our doctrine. We believed that spiritual superiority and technical excellence could overcome material disadvantages. The P-38 proved otherwise. Do you think the war was unwinnable?" the researcher asks. "That is a political question, not an engineering question," Shibata says carefully. "But from a purely industrial perspective, once America committed its full manufacturing capacity to war production, the outcome was determined. This was clear by late 1943, perhaps earlier. The P-38 was merely evidence of a broader reality." The interview is included in the documentary series, which airs in 1974. Shibata watches his segment once, and finds it strange to see himself on television, discussing events from 3 decades past with a calm he did not feel at the time. But the broadcast generates unexpected interest. He receives letters from former pilots, engineers, veterans who remember the P-38 and share his assessment of what it represented. One letter comes from Allison V-1710, former Zero pilot who flew against Lightnings over the Solomons in 1943. He writes, "We were told to close distance quickly and engage in turning combat, where our maneuverability was superior. But the American pilots would not cooperate. They attacked from above, at high speed, and if we turned to the counter, they simply dove away. We could not catch them. We could not force them to fight on our terms. This was frustrating beyond measure. Your report explained why. I wish our commanders had read it." Another letter comes from a Nakajima engineer who worked on the Homare engine program. He writes, "We spent years trying to achieve the reliability that American engines had as standard. We never succeeded. Your analysis was correct. We were optimizing within constraints so severe that no amount of engineering skill could overcome them." Shibata responds to some of the letters. Not all. He is reluctant to become known as a commentator on the war. He is an engineer, not a historian. But the correspondence makes clear that he was not alone in recognizing the fundamental disparity, even if acknowledging it officially was impossible during wartime. In 1987, at age 75, Shibata is interviewed again, this time for an academic oral history project conducted by Tokyo University. The interviewer is more technically sophisticated, interested in specific design choices and engineering trade-offs. They discuss the P-38 inch's considerable detail. "You flew in it," the interviewer says incorrectly. "No," Shibata corrects. "Commander Minobi flew it. I examined the structure and observed the test flight, but I did not pilot the aircraft myself. What was your impression watching it fly?" Shibata thinks back 44 years. The memory is vivid, standing on Rabaul's tarmac in the morning heat, watching the Lightning accelerate down the runway with impossible thrust, climbing away at a rate that defied its weight. "I understood," he says, slowly, "that we were fighting a war we had already lost. Not because the P-38 was invincible, it was not, but because it represented an approach to warfare that we could not counter. American doctrine assumed abundance. Abundant fuel, abundant materials, abundant industrial capacity. They designed aircraft accordingly. We assumed scarcity and designed accordingly. Both approaches were logical, but in total war, abundance defeats scarcity, always." "That sounds defeatist," the interviewer observes. "It sounds realistic," Shibata replies. "Defeatism is giving up when victory is possible. Realism is recognizing when it is not." In March of 1943, at Rabaul, flying a captured P-38, victory was no longer possible. But no one in authority was prepared to accept this reality. So the war continued for another 2.5 years, at tremendous cost. He falls silent for a moment, then adds, "I sometimes wonder what would have happened if my report had been taken seriously. If the strategic implications had been acknowledged, would it have changed anything? Probably not. The momentum of war is difficult to reverse. But perhaps some lives could have been saved. Perhaps some destruction could have been avoided. I cannot know. I only know that I documented what I observed, and it made no difference." The interview concludes. Shibata died 4 years later, in 1991, at age 79. His obituary in the Asahi Shimbun identifies him as a former Nakajima engineer who contributed to several important aircraft designs during the Pacific War. There is no mention of the P-38 evaluation, no reference to the report that accurately predicted the trajectory of the air war 18 months before it became obvious to everyone. The report itself remains in Japanese National Archives, declassified but largely forgotten. Researchers occasionally reference it when studying Japanese assessments of American aircraft. Aviation historians note it as an example of accurate technical analysis that failed to influence policy. But it is a footnote, a minor document in the vast bibliography of the Pacific War. Yet the truths it contains remain relevant, extending far beyond one aircraft or one war. The P-38 Lightning was not the finest fighter of World War II. That distinction probably belongs to the P-51 Mustang, with its longer range and better high-altitude performance, or perhaps to the late-war Japanese designs like the Ki-84, which finally matched American fighters in speed and firepower, if not reliability. But the P-38 was the aircraft that revealed to Japan's best engineers the true nature of the war they were fighting. It was the physical manifestation of American industrial philosophy. Heavy, complex, powerful, redundant, built with margins of excess that Japanese industry could not afford. It was a machine that assumed abundance, designed by engineers who had never been told to optimize for scarcity. And it worked. Not perfectly, the P-38 had its flaws, its limitations, its vulnerabilities. But it worked well enough, in sufficient quantities, operated by adequately trained pilots, to accomplish its mission. It did not need to be elegant or efficient, it only needed to be effective and producible. This is the lesson that Tsuneo Shibata extracted from his examination of the captured Lightning in March of 1943. That war is ultimately decided not by the best designs, but by the ability to produce adequate designs in overwhelming quantity. That engineering excellence without industrial capacity is merely academic. That optimization within constraints is worthless when confronting an opponent without constraints. Lieutenant Hoyt Vandenberg, the American pilot who inadvertently delivered the P-38 to Japanese hands, was posthumously awarded the Distinguished Flying Cross for his service in the Pacific. His body was recovered after the war and reinterred at Arlington National Cemetery in 1949. He was 24 years old when he died, younger than the aircraft he flew, too young to understand the strategic implications of the machine he piloted. The P-38 Lightning he crashed in the New Guinea jungle tail. Number 4, 2-13685, was one of approximately 10,000 Lightnings produced during the war. Lockheed's Burbank factory built them at peak rates exceeding 500 per month. They served in every theater, shot down more Japanese aircraft than any other American fighter in the Pacific, and earned a reputation as reliable, fast, and deadly. Approximately 50 P-38 seconds remain flying today, preserved by museums and private collectors. They appear at air shows, polished and restored, demonstrating for modern audiences what 70-year-old technology was capable of achieving. The sound of twin Allison V-1710 engines at full throttle remains distinctive, unmistakable, impressive. But the true significance of the P-38 lies not in its performance specifications or combat record. It lies in what the aircraft represented: American industrial capacity made tangible, the ability to design complex machines and produce them by the thousands, the resources to build heavy, powerful, redundant systems without worrying about aluminum shortages or fuel constraints, the confidence that comes from abundance. Japan's engineers understood this after examining the captured Lightning. They documented it in detailed reports that accurately predicted the outcome of the air war, but understanding did not translate to capability. Knowing that American factories outmatched Japanese industry did not provide Japan with more factories. Recognizing the strategic implications of resource disparity did not alter the fundamental imbalance. And so the war continued along the trajectory that Tsuneo Shibata calculated on page 47 of his report in March of 1943. American aircraft production increased from 48,000 in 1942 to 86,000 in 1943 to 96,000 in 1944. Japanese production peaked at 28,000 in 1944 and collapsed in 1945 as raw materials and fuel disappeared. By the war's end, American pilots were flying P-51 Mustangs, capable of 440 miles per hour at 30,000 feet, escorting B-29 superfortresses that could carry 10 tons of bombs across 1,500 miles. Japanese pilots were flying Ki-43s and obsolete Zeros, often with minimal fuel, sometimes on suicide missions because conventional attacks had become impossible. The technological gap had widened from substantial to insurmountable, and it had been predictable from the beginning, visible to anyone willing to see it, documented by engineers like Shibata, who understood that wars are won not by courage or tactics, but by the ability to produce, supply, and sustain military forces across time and distance. This is what the captured P-38 Lightning taught Japan in 1943, that they were fighting an industrial war with insufficient industry. That American material abundance would eventually overwhelm Japanese skill and determination, that the outcome was not in doubt, only the duration and cost. It was a lesson that came too late to change anything, but it was accurate, and accuracy in the end is all that engineering can provide. Thank you for reading. For more detailed historical breakdowns, Check out the other videos on your screen now and don't forget to subscribe.